Hello, I am going to talk about the instructional models that help remove scientific misconceptions. And first of all, I do want to talk about the overall misconceptions in science and why we have these misconceptions in science. So there's three key elements that we have for misconceptions in science. First, is students find it hard to understand relationships between information. This could be really broad topics in science that they're very hard for them to really understand the relationships with. An example that I have is things that are subjective, like particles and matter. Particles and matter are so tiny and we can't see them, and explaining this huge world to students might be very, very hard to understand those relationships. Another reason for misconceptions could be preconceived notions. So just their understanding of things before coming into the classroom, and then given all that information and then having to rearrange all that information in their brain based on what they've already known, such as Earth's rotation. When I've talked about Earth rotating, students are like, whoa, like we're moving, and it's kind of hard for them to understand that. And then another one is non-scientific beliefs. One example that I have is just like adaptation of organisms. It's already really hard to understand that organisms are changing to adapt to their environment, and the way that they adapt is really hard for some students to understand based on what they've already known and what their beliefs are. Today, I will talk about three different teaks that I have analyzed as I've taught fifth grade science. And I'm just going to circle them here, and I'm going to talk a little bit more about them in the next slide. So the first teak that is super important is 5.8c, and this is a readiness teak, and it's to demonstrate that Earth rotates on its axis once approximately every 24 hours, causing the day and night cycle and the apparent movement of the sun across the sky. This mastery that you see here is mastery that I've had in an interim assessment in my school. So this was one of the first interim assessments of the school year, and I had 47% of mastery when it comes to this teak. The second teak that I will be using to demonstrate the different models is going to be 5.6a, which is exploring the uses of energy, which is mechanical, light, thermal, electrical, and sound energy. For this, I had 51% mastery. And then the last one is 5.6c, which demonstrate that light travels in a straight line until it strikes an object and it's reflected or travels through one medium to another and is refracted. And for this one, I had 56% mastery. Overall, these are some of the teaks where I've had low percentages when it comes to mastery. And I'm going to talk about some models that I've used to address misconceptions. So the first model that I have used in the classroom that I think is efficient is direct instruction. Now, for the rationale, when I assess mastery either through exit tickets, quizzes, or tests, or big assessments such as interim assessments, it's important to know which teaks are very low performing in order to identify the misconceptions and then make a plan. In this specific example, I have used direct instruction to address big misconceptions that have led to 50% or less of student mastery. Now, the way that I implement direct instruction to reteach TEKs that are very low in mastery is through a model. I do a very direct teacher model of how to answer specific questions. Then I give students some practice time to do a similar one. So this direct instruction can be used to address just really big misconceptions. And one common misconception when we are talking about Earth's rotation and revolution is just misusing the words of orbit, revolution, and rotation. Students often have a hard time, like I said earlier, understanding that the earth is moving and that it's moving in different ways. So when they see a question just like the question that I have here, they immediately think of something really fast, like either a day or 365 days. So the way that I would model it is first by using something that I use in my classroom, and it's called rubies, and I have this up on the walls, and these are the steps for just breaking down questions and figuring out what's the correct answer. So here is an example of the question, and this is how I would model it. So first, we want to make sure that we are using all the different steps of rubies. We're going to read and do the first step of rubies, which is Earth continuously rotates on its axis while also moving on an orbit. About how much time does it take for Earth to make one complete rotation on its axis? So I know that I've already read the question, so I'm going to put a check mark on red. Now I'm going to underline my question to think really, really specifically about what it's asking me. And it's asking me about how much time does it take for the Earth to make one complete rotation on its axis. So I have underlined the question. I'm going to check mark it. Then I'm going to go back to it all and I'm going to box important information. This is where the B comes. So I'm going to box rotation and I'm going to box orbit. And I'm going to think back to what rotation is. And I'm going to write down that rotation is to move on its axis for 1 day or 24 hours. I'm also going to write down that orbit is to go around the sun in 365 days or 1 year. Now I have written down my information, broken it down to the things that I know, and I'm going to start eliminating in my answer choices. So I know that 24 hours might be one of the answers because I have it written down. 30 days has nothing to do with rotation or orbit, so I'm going to eliminate it. 60 minutes has nothing to do with rotation or orbit. I'm going to eliminate it as well. And then lastly, we have 365 days. Now, I'm in between 24 hours and 365 days, so I'm going to go back to my question and I'm going to reread it to make sure that I know what it's asking me for. And it's asking me about how much time does it take for Earth to make one complete rotation on its axis. So it's talking specifically about rotation. I know it has nothing to do with orbit, which is not 365 days. So I'm going to select my answer of 24 hours. Now, knowing all these steps and doing all these steps, I was able to get to the answer. As a teacher, I would push students to go back to the question and to do a similar question using the rubies and using the model that I did. Using the model that I did to go through all the steps. Now, that is one way of direct instruction where I'm just telling them, showing them how to do it, and then they do another one. Okay, moving us along, another instructional model that I've used is facilitative teaching. Now, the rationale behind facilitative teaching is to have a more student-centered learning that allows students to explore topics while teacher guides discussion. Now, the implementation is super important to have pre-made questions to be able to facilitate thinking and using different methods such as think, pair, share to encourage student voice. So if we were to look at this specific example, which I'm going to read, is a student class is observing a pet turtle in a small plastic pool. The students turn on a portable camping lamp that is clamped onto a counter next to a pool. Which kind of energy is used by the portable lamp to produce light? So before I talk about the pre-thought questions and how we're facilitating that learning, here are some common misconceptions. So common misconceptions with students are first understanding that the word produce is to make. If they're not understanding that, they're already going to have a big problem trying to identify the answer to this question. Now, also, students often will say that the lamp produces light energy, it makes light energy, but won't be able to explain that it actually uses electrical energy from batteries to turn on. Now, in order for us teachers to guide that thinking, I do have these pre-thought questions, which are: what information can you gather from the picture? So you're looking at the picture, you see a turtle, you see a lamp. What information is this picture giving you? Then I do want to push them towards talking about producing. What does produce mean? Now, also, I want to push them to think about what is the purpose of the lamp? Why is the lamp even there? And then thinking about the different forms of energy. And then lastly, thinking about where does the lamp can get energy from in order to turn on. So in my classroom, I am a big fan of anchor charts. I think it's a great visual for them to think about all the information that I've thrown at them. So I would push them towards looking at anchor charts. Okay, so you have your different forms of energy. You have mechanical, you have electrical, you have light energy, you have thermal energy, you have sound energy. Think of those different types of energies as you're trying to answer this question. As I'm having them think about that, I use think, pair, share in order for students to discuss with partners. And as they're doing that, I'm circulating, listening to some of their thoughts, and then bringing the class together and having some students share, hey, like, what did you think? Okay, I thought this, and I think that the energy is coming from here. Oh, but I think it's producing this type of energy. So at the end of them sharing with students, I have them share, and then we come together and we try to see what is the correct answer. Now, like I said, I always push them towards these visuals for gathering when they're sharing their information. Another instructional model that I like to use is cooperative learning. Now, the rationale behind this could be in topics such as properties of light that can be hard to understand via instruction. So if I were to just tell them like, oh, light is reflected, light is refracted, it's kind of really hard for them to understand that unless they do a hands-on experiment that pushes them to think and to understand the overall concept. Now, cooperative learning also allows students to hear different views of the topic before developing their final understanding of it. Now, for the implementation, it is super important to strategically place students in the classroom in a good ratio where you have low, middle, and high students so that they can learn from each other. If we're having students that are participating in cooperative learning and they're all very low, it's going to be very hard for them to first start talking and to share a lot of their ideas. So it's important to have like a good ratio in the classroom to be able to share those. Um, within cooperative learning, I also include different methods such as think, pair, share, um, drawing models of things, creating posters, doing hands-on experiments. So in this specific example, if we are looking at the different properties of light and we're trying to determine if light is going to either reflect or refract or transmit, whatever the case might be, before giving students questions like this and before them being able to master something like that, it's super important for them to explore light through the use of flashlights, lasers, prisms, and different mediums such as water and mirrors. So this is when all that cooperative learning comes together. All the students come together. They're exploring via all these different objects, and then they collectively draw a picture or they collectively answer what something in specific that happens to light through a specific medium. Maybe I give them prisms. Maybe I give them a mirror. Maybe I tell them to stand near a window and I have them share ideas among themselves to see what actually happens to light. So, light could either bend, bounce, or go through. Some common misconceptions for light is just a difficulty distinguishing with the different mediums and what it causes to do in light. So a common misconception is the use of water. So in a lot of questions that they're assessed with, they're going to include water. But water can either reflect light or it can refract light, depending on the placement of the objects. So it's super important that when students are exploring this, they're talking and engaging in that discourse, and I'm listening and I'm walking around and I'm asking questions and I'm having other students, higher students or students who have the kind of around the correct idea of light to share more of it so that other students can hear this and they're cooperatively learning all these things. Another common misconception is matching vocabulary definitions of light and what happens to light. So, for example, students might clearly see the light bending through the use of a prism, but they'll still call it reflection. So, in this case, it's also super important that I guide them, where I just tell them, "Hey, look at your anchor charts. What do you see? Is it matching what you and your partner are saying? What do you think? How can you fix this?" And that cooperative learning can also be used to address those misconceptions within themselves. So in conclusion, the instructional methods, they can differ depending on where students are. If students have been assessed in the mastery and the mastery is very low, then a direct instruction approach might be a good option. This is what I have used in the past, and I feel like I've been successful at it. Now, if students are being introduced to information or they're exploring their views of it, cooperative learning and facilitative learning might be a good option. We as teachers have the power to pivot towards using different methods that will meet students where they're at and address the misconceptions productively. So those are three that I've used in my classroom. And sometimes I find myself, like I've said, just changing the methods because I want to make sure that I meet students where they're at. Thank you.